I will now introduce our next speaker, and this is Will Moulder. William, who is from MIT Lincoln Lab, prominently featured also in Rebecca's talk. For those of you who don't know, Lincoln Lab is a federally funded research and development center. It's operated by MIT under contract with the United States Air Force. It's physically distant from MIT, and that enables us to do the kinds of government research that we may not be able to do on campus, but there is a strong and growing connection between what Lincoln Lab does and what we do here at MIT as well. And I know that Will and his colleagues are doing some really interesting work in terms of deployable antennas and SmallSat antennas, which is of great interest to the satellite industry. And I know that because the satellite industry asks us about it a lot. So I will tap dance a little bit longer while he gets mic'd up. I'm not going to tell jokes because I'm not funny, as my wife tells me. But with that, Will, take it away.
Thank you very much, Ron. Good morning, everybody. Thank you for attending this session, hearing about the work that we're doing on deployable antennas for small satellites. As Ron said, my name is Will Moulder. I'm a technical staff member in the RF technology group at MIT Lincoln Laboratory. I'm going to begin with a definition. So when I talk about small satellites in this presentation, I'm actually talking about a subset of what maybe some would call small satellites. I'm talking about micro and nano satellites, so platforms with a mass of less than 100 kilograms. And you know, a statement that I don't think is going to be breaking news to this room is that, you know, this has had these kind of platforms have had a profound impact on access to space, where in decades past, you know, space was a domain for basically state entities with big budgets. Micro and nano satellites, you know, cube satellites and similar sort of platforms have enabled universities, small companies to bring forth all sorts of, you know, innovative and new applications using this domain. And this trend is really apparent when you look at this chart. This plots nanosatellite launches by year. And what you see is that not only the number of launches has grown dramatically in the last 10 years or so, but that universities and commercial entities are really leading the charge. And I think that the result of that is there's been a real diversification in the applications and use cases that have emerged. And I'm sure that one could probably fill the entire 30 minutes talking about the different applications that have emerged. I'm going to focus, though, on applications that exploit the radio frequency spectrum, or RF applications. So applications like imaging radar, where you now have several companies that are selling really impressive synthetic aperture radar data that was taken from constellations of CubeSats. Scientific sensing is another important application here. A great example of that is MIT's AeroVista program, where next year there will be 2 CubeSats that are launched with the intent of sensing radio emissions from Earth's auroras. These are emissions that are blocked by the ionosphere, so are unable to be sensed from Earth. And really, this is only possible from kind of a financial and risk point of view because of kind of the rise of CubeSats, because of the lower barrier that they present. Weather monitoring is another interesting use case. The weather forecasts that we all depend on every day have as one of their very important inputs microwave radiometer measurements that are taken from space. And right now, those measurements are taken from very large, expensive, multi-billion-dollar platforms. And what programs like TROPICS, which is led by MIT Lincoln Laboratory, what those kind of programs are showing is that some of that data can be taken with CubeSats just as effectively. And of course, that would be a game changer because you would see a tremendous reduction in cost per sensor, and you would be able to have many more in orbit, greatly improving the revisit time. Spectral monitoring is a use case that has applications in terms of tracking commerce, tracking shipping vessels, tracking air traffic, but also many DoD use cases as well. And then finally, communications is a really attractive use case for these kind of platforms. I'm talking mostly about relays or systems that try to exfiltrate data back down to Earth. So a great example of this is the Marco CubeSat that JPL developed. This was a CubeSat that basically was able to beam data down from Mars to Earth. And again, what makes microsats and nanosats such a favorable platform for this is these communication nodes are often not the star of the show, not the star of the mission. So the fact that you have this inexpensive platform to use is really attractive. So when I look at these examples as an RF engineer, I'm just amazed at what the community has been able to do in the last few years in terms of miniaturizing very complex payloads such that they can fit on these very small platforms. And I think it's incredible work. And I guess one challenge that jumps out to me as sort of still remaining in this space is that you still need large antennas. I would make the maybe somewhat too broad statement to say probably all of these applications would benefit from having larger antennas. Generally, these applications would demand the finest resolution and the highest gain you could provide. So, basically, the larger we can make these antennas, the better we're going to be able to perform these applications from small platforms. And, one of the challenges with antennas is that often you can't miniaturize them. If I have a requirement for a beam spot size on the ground or for an antenna gain to close some kind of data link, there's a physical limit on how small the antenna can be. And often that physical limit is multiple times the largest dimension of one of these platforms. And so it really highlights the need to think about deployable antennas, which, put quite simply, are antennas that start small, that are compact when they're stowed and launched, and then, somehow become large once they're in orbit. And there's a number of ways that are being examined to do this. Probably the simplest way to think about it is something like what we have depicted here, where maybe you have a large panel-based antenna that starts out folded up against the spacecraft and then unfolds once it's in orbit. We'll talk about a couple different ways to deploy large antennas, including one like that. Now, why is the area of deployable antennas an area of active research? Deployable antennas, to me, is a field that sounds really simple, but ends up being really challenging. And I've listed why it's a challenging field. The first is kind of the obvious one. We have to come up with some way of compactly stowing a large aperture and reliably deploying it. And that second aspect is really a challenge from a mechanical engineering point of view. This is a graphic from a program that is actually going to start next year called Cruiser that Lincoln Laboratory is going to lead. And in Cruiser, we're going to build a scanning reflector array antenna that operates at 58 gigahertz. Well, at 58 gigahertz, the wavelength's about 5 millimeters, so a fraction of a millimeter in sort of deviation from the intended surface is going to have a significantly damaging effect on the antenna pattern. Other challenges are that we need antennas, when they're deployable, that are both lightweight and rigid. Otherwise, when these large antennas are deployed, they're going to have an adverse impact on the spacecraft's dynamics. When we talk about active antennas, when we talk about antennas like phased arrays, antennas where we have amplifiers and or phase shifters embedded within the aperture, we really have to worry about power consumption when we talk about fielding these on micro and nano satellites. The power budget of say, a nanosatellite is quite modest. And when we think about large arrays, at 10 gigahertz or more, we end up with thousands of elements. And it's, you don't have to be burning very much power at each element, say per amplifier, to chew up the power budget of a small satellite. And then a challenge that goes along with that is thermal stability. If you have devices in the aperture, those devices are going to generate heat. And we have to think about how to get heat off the aperture, or we have to think about how to design the aperture such that it can get hot and not deform. So this is why I think that deployables are an area of active research, or these are sort of the challenges that the research community faces. At Lincoln Laboratory, We've been doing some research in this area in the past several years. I'm going to talk today about a handful of projects that I would call early stage research in this domain. So maybe with the exception of the first one that I'll talk about, all of these are probably TRL 3 or lower. But when I talk about these projects, I think we can group them into 3 different buckets. I'll talk about an antenna that is aimed at low frequencies. So basically one reason that you need an antenna to be large on a small platform is if it's operating at lower frequencies. So think like the lower megahertz spectrum. And the reason for that is that at low frequencies, your wavelength is really large. And antenna generally needs to be on the order of the size of the wavelength, so a large wavelength applies large antenna. I'll also talk about highly directive antennas. So imagine like dish antennas that we try to field on say, CubeSats. And then I'll talk about highly directive scanning antennas. So antennas that not only have a tight focused beam or maybe a small spot size on the ground like say this dish would, but that can electronically scan their beam, that can basically change the direction that the beam's pointing without physically moving. So I'll begin by talking about an example of an antenna for low frequencies. This is a deployable vector sensor antenna that will be part of MIT's AeroVista program. And so I mentioned this a little bit earlier. This is, again, a pair of CubeSats, Aero and Vista, that will sense radio emissions from the Earth's auroras. And as part of the system that we need for the sensing, it has these deployable antennas. So it has these 2 crossed loop antennas that are stowed in a 1U volume, so that's a 10 centimeter cube, and they telescope out to a length of 4 meters. And of course, again, this length is needed because we're dealing with relatively low frequencies here, low megahertz spectrum. So you have these cross loop antennas, and you also have this monopole antenna that sort of pops up from that volume. And what's neat about this configuration is not only does it allow researchers to sense the emitted spectrum of the auroras, but this kind of cross loop plus dipole configuration allows location of the emissions, so that basically researchers can kind of map where these emissions are coming from. It also allows for sensing of the polarization. Now, AeroVista is targeted for launch next year in 2022. Of course, the actual antenna and hardware that will go up there is under development. There has been some ground testing of prototypes. This is an example of a balloon test where an antenna similar to the one that will eventually be used was put on a high altitude balloon. It was used to geolocate some beacons on the ground, and that was very successful, providing confidence sort of for this team as they approach the eventual launch. So I'm going to talk now about a different class of antennas where we're doing some work. These are highly directive antennas with fixed beams. So, the example I gave when I introduced this category is something like a dish antenna. This is an example of an inflatable reflector that Lincoln's looked at. The idea here, as you might imagine, is that this reflector is basically a balloon. So it starts out, not inflated and kind of tightly packed together. And then the idea is that once it's in orbit, some kind of a gas is used to inflate it, and it's much larger than the platform that hosts it. So I believe that this prototype was stowed in something like a 1 to 2U volume and will deploy to a 2.7 meter overall diameter. Now, the balloon is made of a non-conductive material, basically an RF transparent material, and the way that the reflector's formed is that the underside of it, as sort of referenced on this diagram, is metallized, making kind of a conductive bowl shape. And then on the opposite side, there's another metallized, smaller bowl that serves as a subreflector. And so the idea is that there's a feed in the center, a feed, inside the spacecraft that illuminates the subreflector, which in turn illuminates the main reflector. Now, the team at Lincoln Lab built a prototype unit, tested it in an antenna chamber, did some other sort of mechanical characterization, successfully proved out the concept. I would encourage any other antenna nerds like myself to go check out sort of the quantitative results in the paper reference down here. I know it's a little hard to see, but if anyone wants more information, be sure to send me a note and I'll happily point to it. But overall, successful measurement of a very interesting concept. So another interesting concept in this area is actually a collaboration between Lincoln Laboratory and the Aero Astro department at MIT. So we're working with Professor Zachary Cordero, who I believe you'll hear from later today, to try to leverage some of the really interesting CNC wire bending work that his team is doing to conceivably make large reflectors in space. So for those who aren't familiar with his work, he has a team looking at use of this wire bender, which just takes a spool of wire and uses an algorithm to intelligently bend this wire as it's fed through these pair of wheels here. And if properly planned, you could form this wire into some kind of arbitrary and complex three-dimensional shape. And in my group, one relevant shape would be to form it into a reflector. And so the vision is that one day you could use something like this and you could basically launch a big spool of wire and in space make some very large reflector antenna. So we're working with Professor Cordero's team to try to prototype and measure a test article, basically a test dish, and see if we can show this as a viable concept. So the last class of antennas I'll talk about is really kind of what I view as the frontier in research on antennas and SmallSats, and that is highly directive scanning antennas. So these are antennas that can point a focus beam but can electronically scan them. So for those who are familiar with phased arrays, technology kind of along those lines. In general, any kind of antenna that does this is some kind of array antenna, whether that's a phased array or sort of a space-fed array or some set of antenna elements that are in a grid, and they are intelligently excited such that their radiation sums coherently in some desired direction. And one of the challenges in putting array technology on small satellites is that arrays can be fairly complex. That translates generally to a lot of power consumption. That translates generally to higher masses that would typically be desired, in these kind of applications. So I'm showing some examples of arrays and their area density, their masses per square meter, and there are a lot of examples of arrays that are 100 kilograms or more per meter squared. MPAR is a cutting-edge, highly integrated array that Lincoln Laboratory has worked on. That was 60 kilograms per meter squared. So we're looking at arrays that are much lighter than that. We've found that we've done some analysis to show that really where you need to be is something on the order of 6 kilograms per meter squared or less. And we'll talk about a few examples of kind of emerging technologies to help us get there. So the first one we'll talk about is one called lightweight ESA, which was a study that we did at Lincoln to try to understand if we look at kind of almost a conventional phased array construction, and we tried to suck all the mass that we can out of it. Basically, we tried to do all the light weighting we can. What kind of capability and what kind of mass could we really achieve? And the idea is that it would be built in panels. Exploded view of a panel is shown here. It would be unfolded from a satellite bus, kind of shown in the graphic to your left. And for this particular application, the target application, the idea was that you wanted a long array, so panels that kind of unfolded and made a very long array. And so one of the real kind of revelations that the engineers that were working on this sort of came to was that when they looked at the mass that had to be there, one of the real killers was the antenna substrate. To basically get an antenna with adequate beam bandwidth and efficiency, it needs to have a reasonable amount of thickness, and that material supporting the antenna was a real killer in terms of the mass. So one of the innovations they came up with is this castellated substrate where part of it's cut out and basically you end up with sort of a void in the middle of the assembly. And the nice thing about this assembly is it's fully compatible with printed circuit board technology. So if you were trying to make a number of these panels, you don't need to rely on a huge amount of hand assembly. So this is a prototype of the lightweight AESA. You can see a close-up that shows the castellated substrates. It may be a little hard to see with the color contrast, but if you look closely, you can see part of the substrate is etched out. We did some testing with it. This is an example of some antenna patterns, and once again, I point to the reference here for anybody who's interested in more technical detail. One concept for going even lighter is to use flexible materials. So we also looked at a prototype we called the Rigid Flex Antenna Array, or RFAA. The idea behind the RFAA was to say, let's take a flexible circuit material. So think, basically like a polymer that is like as thin as a sheet of paper. And let's let that span the entire area of the array. That can carry all the signal distribution, that can carry all of the, the power lines, things like that. And then we populate this array with islands of rigid substrate. And these rigid islands serve two purposes. First, they provide a substrate for the antenna. And second, they rigidize a small part of the area so that we can attach, soldered-on components to the backside. And as this flexible circuit is bent, these components are basically not going to pop off. And in addition to being very light, one of the nice things about this technology is it opens itself up to more stow and deployment options. It could be rolled and unrolled, not just folded. So we built a prototype of this. This is the prototype on your left side. You can see that we rolled it up. We tried to beat it up as much as we could. This is an antenna pattern that we measured. The blue curve is what we measured before we did any roll-unroll testing. The red dash curve is what we saw after we wrapped it around an 1.5 inch pipe and rolled and unrolled 50 times. And you could see almost no difference. So this is to show that basically it really can stand up to the abuse that you'd see when you roll and unroll it. The last effort I'd like to talk about is called DESRA, which stands for Deployable Electronically Scanning Reflector Array. This one's a little bit different than the phased arrays that I've talked about to this point. The overall goal is the same. The overall goal is to provide a highly directive electronically scanned beam, but the big difference is that whereas a phased array distributes RF signal to each one of its elements actually within the panel of the array, what DESRA does is it has a feed similar to what you'd have with like a reflector antenna. That feed is going to illuminate this flat surface. And this flat surface is populated with antenna elements that are retrodirective. So in other words, they reflect whatever radiation they capture. And what we do is we embed really simple, low loss, low power consumption switches into each element. So at the element level, we can change the reflected phase. And we can set up a holographic phase pattern, kind of like what was shown here, such that when the illumination hits the surface and reflects off, a coherent beam sums in some desired direction. And so that's how we're able to do the electronic scanning with this kind of system. Now, why would we want to do this? It's well known you can do scanning with phased arrays. Why do something like this? And the answer is that although phased arrays are definitely an interesting area of active research in this domain, definitely have kind of really attractive performance characteristic for SmallSat applications, there are some challenges. One of the big challenges is one I mentioned several slides ago, that's power consumption. Imagine you have an X-band array, say 10 gigahertz, 1 meter aperture. Long story short, you end up having thousands of elements. And so if you think about, if you think about having thousands of elements, it means thousands of amplifiers. Even if each one of those is pretty efficient, it adds up pretty quickly. And again, you start to chew up the power budget of a SmallSat. So power consumption is a big challenge with phased arrays. A challenge that goes right along with that is thermal management. If I have amplifiers on the aperture, they're using power, they're getting hot, and that heat has to go somewhere. And then finally, cost is a consideration here. I think that, again, if you go back to the days before the rise of micro and nano satellites, cost would almost be a non-factor because the array would still be way cheaper than the platform. But now that we're talking about universities launching these things, we're talking about satellites that are, that are on the order of, just a regular old house in the Boston metro area in terms of cost. We have to think about the cost of phased arrays, and it's very high when you think about some of these applications. So what DESRA does, because it has no amplifiers in its aperture, it only has these low loss switches at each element. Power consumption is extremely low. As such, thermal management's very easy because it doesn't get hot. And by the way, since we don't have all of these complicated electronics in the aperture layer, which are kind of notionally depicted on the left-hand side of the slide, cost is a lot lower. And so we've explored this concept for a couple years now with some internal funding. We built a prototype here. So this is a 2.2 square meter implementation of DESRA operating at 9 gigahertz. For those of you who maybe work in antennas or phased arrays, I think you'll appreciate as a testament to how low cost DESRA is, the fact that we're able to prototype an aperture this large at this frequency on kind of internal seed money. These are some examples of electronically scanned patterns. So these are patterns where we have electronically pointed the beam to different angles, 0 degrees through 45 degrees. Looks very much like a pattern that you'd expect with a phased array. One of the interesting design details of DESRA that I don't go into in much detail in this presentation, but I'm happy to talk more offline if needed. So there's an image in the lower left-hand side of the slide that shows kind of a cross-section of DESRA. It has these embedded aluminum grids, which allow it to basically be very rigid. And these aluminum grids, though, are very sparse, so it allows it to be very lightweight. And it's also allows the entire assembly to be thermally conductive. So the idea is that when it's, say, illuminated from one side by the sun or otherwise heated from the other side, it doesn't warp. And so there's a lot of interesting aspects about DESRA. Again, if there's more interest, I'd be happy to talk offline. Hopefully we have some publications out on this soon that we can point to and get this out to the broader community. So one aspect of the research that we did for DESRA, which is applicable to not only DESRA, but like the array concept I showed, or really any sort of array or panel-based antenna, is some of the work that we've done in trying to understand what would go into the deployment system. So our team working on DESRA came up with this really simple but very effective deployment scheme. The idea is that this would go on something like an ESPA class platform. So picture like the size of a mini fridge or something, and would open up to maybe the size of a small kitchen table. But it's really scalable to any size platform. But this is the EDU that we built, showing that the deployment scheme works. What we're working on right now is actually populating this with the DESRA panels that we showed on the previous slide to try to see how reliable that deployment is and if it's good enough basically to function electrically. So I think I'm just about out of time, but I guess I'll just say in closing, I don't think I need to emphasize the impact that SmallSats have had on the community. Huge impact. I think a big challenge is deployable antennas. We're doing a lot of interesting work on this, and I'm happy to talk more offline about technical details, or if there's interest for collaboration, I'm happy to talk about that as well. So that's all the content I present. I don't know if we have time for questions, but thank you for your attention.
We are heading into break, so we definitely have time for a couple of questions if anybody has one. Yes, you have to have the microphone.
Hi, so thank you very much for that. It was interesting to hear you talk about, well, I was happy to hear you talk about Aero, the Vista. I was going to mention it in my talk. I'm the project manager for that project, and we're having a hard time right now with the deployment. We have we have the vector sensor. It's great, it works well, but like getting it out of the 6U CubeSat is really a struggle. And I'm wondering what your thought, like if the lab is working on that, how much the lab will be focusing on that aspect of all of these systems. Because sort of like the CubeSat thing, like I alluded to, they're like low cost, but it's still really hard to get these things out of the CubeSats, even if you've got it deployed, working, and stowed working. That it's the transition that's the trick. So.
Yeah. Well, so yeah, I think that that your comment emphasizes the challenge there is in deployables. Again, I feel like it's one of those things that sounds simple, right? It's just you pop this thing out. How hard could it be? But it.
Empty, and then when you put all the cables in it.
Yeah. To your specific question on what the lab is doing to improve deployment, so I'm not involved with the AeroVista program. I presented those couple slides on somebody's behalf. I do know that the lab does have experts in this field that, like, all day they think about how to deploy stuff on satellites. So if there is a discussion that should happen, let me know and we can put you in touch with the right folks at the lab.
So is your group working, even if you just put the AeroVista aside, I'm thinking about the other thing that
Yeah.
you're showing. Is there a connection between the mechanical deployment folks and then what you're doing?
Yes, absolutely. So my group is the RF technology group. So we do all the electrical design, but we partner with the mechanical engineering groups, and we have experts in those groups who focus on deployables. So particularly like in the Desert program, we had as a co-PI a mechanical engineer who focuses on deployables. And again, I can't speak for the specifics going on in AeroVista, but if there are conversations that should happen with subject matter experts in this area, we do have experts at the lab, and I'm sure we can facilitate those discussions.